The quadrilateral ABCD is a trapezium in which AB and DC are parallel. With respect to the origin O, the position vectors A, B, C are given by OA equals this, OB equals this, and OC equals this. Given that DC equals 3 times AB, find the position vector of D. All right, let me just roughly draw this trapezium first to make sense of this question. So AB is parallel to DC, and DC is 3 times of AB. So this could be AB and then C and then D. All right, so for part A, we're going to break this into the difference of its position vectors, which is OC minus OD equals to 3 times, break this into the difference of its position vectors, so OB minus OA. So OC is 2, 2 minus 3 minus OD equals 3 times B minus A. In fact, before I start, I should write all of these position vectors in form of column vectors. So minus 1, 2, 3. Then OB is 1, 3, 1. And OC is 2, 2 minus 3. Right. So OB minus OA would be 1 minus minus 1, which is 2. Then 3 minus 2, which is 1. And 1 minus 3, which is minus 2. Now we triple this and send it to the other side. 2, 2 minus 3. Minus 3 times 2, 1 minus 2 equals OD. Let's add these together and get our answer. We have 2 minus 6, which is negative 4, 2 minus 3, which is negative 1, and then minus 3 plus 6, which is a 3. So this is the position vector for OD, minus 4, minus 1, 3. And we write it as minus 4i minus j plus 3k. Yes, the first part is done. Part B, state a vector equation for the line AB. It's pretty straightforward. We write R equals, choose either the coordinate of A or coordinate of B. I'm choosing A, which is minus 1, 2, 3, plus lambda or mu lambda. And now you use the other coordinate, which would be B, and then minus subtracted from the same coordinate A. So B minus A is 1 minus minus 1, which is 2. In fact, we already found B minus A earlier. This was B minus A. So let's write that again. 2, 1 minus 2. So R equals minus I plus 2j plus 3k plus lambda 2i plus j minus 2k. Let me check the answer real quick. Okay, it's correct. Part C, find the distance between the parallel sides and hence find the area of the trapezium. All right, so distance between the parallel side would be this distance, but in terms of vector, what we'll do is we already have this vector line AB. We have the equation of this vector line AB, which is this, and we're going to find the perpendicular distance either from point C to this vector line or the perpendicular distance from this point C to this vector line. So if I'm choosing C, so the vector line is known to us. It is R equals for minus 1 plus 2, okay, sorry, minus 1, 2, 3 plus lambda 2, 1 minus 2. And we have the coordinates or position vector of C as well. C is 2, 2, minus 3. Okay, this is point C. And we need the height, this height from C towards this line. All right. So the perpendicular distance, what we do, we first name this foot of the perpendicular. Let's name it X. So we need the position vector of C, which we already know is 2, 2, minus 3. Then we need the position vector of X, the foot of perpendicular. Since it passes through the vector line, it will have the same position vector as the vector line, which is this -1 plus 2 lambda, 2 plus lambda, and 3 minus 2 lambda. From these two, we find the vector Cx. So Cx would be Ox minus Oc, which would be, let's subtract these two, we'll get a -3 plus 2 lambda, then a lambda, and then 6 minus 2 lambda. Okay, now what we'll do, we'll use the dot product of Cx and the direction of the line passing through AB, that is this direction. The dot product between these two would be 0 because these are perpendicular lines. So the dot product between Cx and direction of the line passing through AB, which is 2, 1, minus 2, is equals to 0. So dot product of -3 plus 2 lambda, lambda 6 minus 2 lambda, dot 2, 1, minus 2 should be equals to 0. We will apply the dot product, equate it to 0, and that should give us the value of lambda. Okay, let's apply the dot product. So 2 times -3 plus 2 lambda is -6 plus 4 lambda plus lambda minus 12 plus 4 lambda equals to 0. We're getting 9 lambda here and 18 here. So we're getting lambda equals to 2. Okay. And we need the perpendicular distance from C to the vector line. So we will first find this vector Cx by substituting the value of lambda in Cx. This was Cx. Substitute lambda here and then find its magnitude. That's going to give us the perpendicular length. Okay, so Cx is, with lambda is equals to 2, Cx would become -3 plus 4, which is 1, then 2, then 6 minus 2 times 2, that's also a 2, and then the magnitude of Cx will be square root of 1 square plus 2 square plus 2 square, that's a square root of 9, which is a 3. So we know that the perpendicular distance between these two parallel lines is 3. This is 3, or this is 3. Now the formula is half times height, which is 3, times sum of parallel sides. That's the formula for area of trapezium. Okay, do we have AB? I think we did find AB. Yeah, this is AB. 2, 1, minus 2, because AB is OB minus OA, which we've already found earlier, and we take its magnitude. So that will also be square root of 9, which is 3. So let's write that here. AB is already known. We found it in the first part from OB minus OA, 2, 1, minus 2. And its magnitude would be square root of 9, which is 3. So one parallel side is 3. And for DC, we were told that it is 3 times of AB. So 3 times 3 is 9. So this length would be 9. So 9, and let's find the area. There, that'll be 12 divided by 2, 6. 6 into 3, 18. So 18 is the area of this trapezium.